Okay, welcome to section 5.6, rational functions. And our learning objectives for this section are to find the domains of rational functions, identify their vertical asymptotes, their horizontal asymptotes, identify any holes that might be in the rational function, and graph them. All right, so let's get started. First, let's talk about what it means to be a rational function. A rational function is a quotient of polynomial functions, where the denominator, q of v, cannot equal 0. So what does that mean? It means we need to make sure that the numerator is a polynomial and the denominator is a polynomial. Remember we talked about in the previous video about what it means to be a polynomial, and it means you need to have real number coefficients and whole number positive exponents bigger than 1. Okay, so let's look through these examples and see which of these are rational functions, which means we're checking to see if the denominator and the numerator are both polynomial functions. So let's look at the first one, A. The numerator is t squared minus 2t plus 3, and the denominator is t plus 1. Yep, those guys are both polynomials, so this guy is rational. It's a rational function. Let's look at B. The numerator is e to the k. Already we're in trouble. This is not a rational function because e to the k is not a polynomial. All right, let's look at C. Actually, why don't you take a second to look at C and decide for yourself. Pause the video for 1 second. Decide if you think that's C and D. Decide if you think that those guys are rational functions. All right, did you come back? Did you get the C was not rational because of the square root of z in the denominator? Right? Not rational. Because remember, square root of z is like z to the 1/2. That's not a whole number. Square root of z is not a polynomial. And what about D? D is rational. 3 is a polynomial. It's kind of a boring polynomial, but it's a polynomial. And V is also a polynomial. So this guy is rational, right? 3 is like 3 times V to the 0 and V to the 1. So those guys both are polynomials. All right. Now we have a feeling for what rational functions are. Let's talk about what we need to learn from them. Well, the first thing we're going to focus on is the denominator. The denominator of the rational function tells us two things. It can tell us about the domain, and we've talked about this before, and it can tell us about the vertical asymptotes. So the inputs that are excluded from the domain of the rational function are where the vertical asymptotes occur. So those guys are partners. If it's not in the domain, then there's going to be a vertical asymptote there. What does that mean, a vertical asymptote? Well, that's what happens when we try to divide by 0. It just shoots off to infinity or shoots down to negative infinity because you're dividing by smaller and smaller and smaller values. So graphically, it looks like a vertical dashed line that the function cannot cross. Okay, you can't cross it, you can't touch it. When we write vertical asymptotes, they're vertical lines, so they're just of the form x equals a number, right? So let's look at an example to put this all into play. All right, here's our example. F of x equals x minus 7 over x squared minus 4. The first thing we're going to try to figure out is which values are excluded from the domain of f of x. So for it to not be in the domain, that's where the denominator equals 0. To figure that out, we need to solve for x squared minus 4 equals 0, and then we want to exclude those guys. Well, you could use a quadratic formula to solve this, but I think I'm going to use the square root method. I'm going to add 4 to each side. That gives me x squared equals 4. And remember, the square root method only works when there's no linear term, no something times x term. Take the square root of each side. You get x, something stopped working. X equals the square root of 4, which is plus or minus 2. So those are the two values that are excluded from the domain. So x equals 2 is excluded. X equals negative 2 are, these guys are excluded. So if we wanted to write down our domain in interval form, it'd be minus infinity to minus 2, not including it, union minus 2 to 2, don't include the endpoints, union 2 to infinity. That would be the domain of this function. Oh, look, I accidentally wrote that ahead of time. We're just going to draw a little arrow. What's the domain of f of x? There it is. All right, so what are the vertical asymptotes? I don't know why I capitalized that, but whatever. Well, the vertical asymptotes are exactly these two values. X equals 2 is one vertical asymptote. That's a vertical line, x equal to 2. And the vertical line, x equal to negative 2, is the other one. Let's look at a graph and we can kind of see what's going on here. So this is a graph of the function that I graphed on Desmos. And we can see that if we look down at x equal to 2, that's this line right here, you can see that the function does not cross this line. It gets really close to it, as close as you want, but never crosses it. And that, of course, is x equal to 2. That's this guy. And x equal to minus 2 is this guy over here, right? Same thing that's going on at x equal to minus 2. So that's what it means to be a vertical asymptote. So you can kind of see as the graph goes along, if we're starting at negative infinity, we come in as we get to negative 2, we shoot up to negative infinity. Then we're up here and we're doing a kind of a quadratic-y thing looking there. And then we come back and start at negative infinity and come in. So that's what vertical asymptotes look like. And those, again, are exactly the values that are not in the domain. All right. It says video 2, but I think we can keep going. Let's just keep going. I'm just going to cross this out. This is still video 1. We've only been going for about 6 minutes. All right, so what does the numerator tell us? The denominator told us the vertical asymptotes and the values not in the domain. The numerator tells us the horizontal intercepts, right? Where the numerator equals 0 and the denominator doesn't is going to be where it crosses the x-axis. We also call these guys roots and zeros. Remember, those are the 3 synonyms there. All right, so let's look at our same example that we had before, x minus 7 over x squared minus 4, and let's find the horizontal intercepts. We want to find where f of x equals 0. Well, this is a little bit of an algebra trick. You got to be a little careful when you do it. If we set the whole thing equal to 0, x minus 7 over x squared minus 4 equals 0, what we can do is we can actually divide both sides by x squared multiply both sides by x squared minus 4 to cancel out that denominator. And 0 times x squared minus 4 is still 0. So we end up getting, I didn't leave myself quite enough space, x minus 7 equals 0. So that's sort of the trick, is that you really can just solve to see where the numerator equals 0 because you can always just multiply out that denominator. Well, x minus 7 equals 0 when x equals 7. And so that's our horizontal intercept for this one, is over 7 up 0. Let's go ahead and mark that on the graph. You can kind of see it's right here. That's the only place that it crosses the x-axis. How do we find the vertical intercept? Well, this is the same for all functions. To find the vertical intercept, you find where the x is equal to 0, or you evaluate f of 0. F of 0 is going to be equal to 0 minus 7 over 0 minus 0 squared, even, minus 4, which is equal to minus 7 over minus 4, which becomes 7/4. So that's the point over 0 up 7/4. And let's mark that on the graph too. Right there, that's our vertical intercept. Vertical intercept here. Horizontal intercept here. And of course, we still have our, that we had from the previous graph. I didn't draw them. Here is our vertical asymptotes. All right, so we found out a lot of things about this graph. From the denominator, we get the vertical intercepts and the exclusions from the domain. From the numerator, we get the horizontal intercept. And by plugging in x equal to 0, as with any functions, we get the vertical intercept. All right, let's try one more example here. So let's do this same process, all the things that we've done with this example. So what is the domain? Well, remember, this comes from the denominator, right? We look at the denominator for this and we see where x squared minus 64 equals 0. And we exclude those values. Using the square root method, we get x squared equals 64. Let's take the square root of each side. X equals plus or minus 8. So those guys are the exclusions from the domain. So the domain is equal to minus infinity to minus 8. Don't include it. Union minus 8 to 8. This is a lot of weird infinity signs, kind of like an 8 on their side. Union 8 to infinity. All right, so there's the domain of our function, excluding negative 8 and 8. So where are the vertical intercepts? Well, negative 8 and 8, right? X equals 8 is 1, and that's a vertical line. X equals negative 8 is another one. What are the horizontal and vertical intercepts? Remember, the horizontal intercepts are where the numerator equals 0. Well, in this case, the numerator is just equal to x, so x equals 0 is our horizontal intercept. So that's going to be the point over 0 up 0. And luckily, that's going to be our vertical intercept as well. But what the heck, let's just find t of 0. That's the process. And that's equal to 0 over 0 squared minus 64, which is 0 divided by negative 64, which is 0. All right, so let's sketch what we know so far. I didn't graph this guy in Desmos. So we can't draw too much, but we can do a few things here. So let's put a grid down. And let's get a different color. And let's go ahead and put our vertical asymptotes in. So we have 8 and minus 8. We know there's going to be vertical asymptotes there. We know it goes through 0, 0, and that's pretty much all we know at this point. So it's going to be pretty hard to draw a graph of this without using Desmos. So what I'm asking you guys to do right now is looking at this base that we put down, go ahead, stop the video, go to Desmos and look at the graph of this function and find all these different pieces.